I want to say how pleased I am to be here today and talk with you guys, because I really appreciate the initiative of trying to join forces for analyzing these data sets. So this is really exciting for me. So thank you for organizing that. This is great. So I will talk about QUBIC today, which stands for the QU Bolometric Interferometer for Cosmology. So some of you may have heard about it quite a lot. Some others know. So I will try to explain you a little bit what it's all about and the specificities of QUBIC with respect to other instruments observing CMB polarization, because QUBIC is very different. So currently QUBIC is also very different because it's located on a boat. But this is just because we're traveling from France to Argentina, where the instrument will be installed very soon. So we're in the middle of the road now, closer to Spain than Argentina for now, but making significant progress. So we're very happy that the instrument is going now to the site. So QUBIC is this collaboration between all of these institutes located in these countries, mostly I would say France, Italy, Argentina, Ireland, UK, and just a few people in the US. And the site will be in Argentina here, not far from our Chilean friends, but on the Argentinian border at 5,000 meter altitude. And the picture you can see behind me is the picture taken at the site. So QUBIC is intending to address the primordial B-mode challenge with very specific technique called bolometric interferometry. So the weakness of the signal, we have a focal plane with 2000 TSs with a multiplexing readout of a factor 128 to 1. And I will show you later that we have simulations that show that we can expect to have a sigma on the effective R of 0.015 with 3 years. So the specificities of QUBICs come now with the specific technique to deal with instrumental systematics, because QUBIC is, before anything else, an interferometer with 400 apertures. This means that our beam is the synthesized beam of an interferometer with an angular resolution of less than half a degree. And also we have a very specific optical design that I will shortly discuss that allows us to achieve a very low cross polarization. Regarding foregrounds, we have 2 bands, but that's not particularly original. But what we have, which is really fun, is that because QUBIC is an interferometer and because this synthesized beam that I was mentioning depends on frequency, QUBIC also has this Spectro-Imaging ability, which means that we can form up to 4 or 5 sub-bands in each of the 2 bands I just mentioned here, which means that we can have access to a more local estimation of the foreground colors. Okay, so this is the outline of my talk. I will try to go rather briefly on the QUBIC concept because I would like to show you some results. And you have here a picture of a subset of the collaboration a few years ago when people were meeting each other. It happened a long time ago. Okay, so let's start with the QUBIC concept. So the idea is that the first element in QUBIC, of course, all of this is in a cryostat, but I want to discuss the concept here. The first element that takes electric field from the sky is our half-wave plate, which is a stepped half-wave plate that will rotate so slowly, not continuously, which modulates the polarization. Then we have a polarizing grid, which is very early in the optical chain, which means that we're rejecting half of the power, which is the cost of this design. And then we have these horns that really are the interferometric part, which act like pupils in a piezointerferometer. So then we just focus the image of all of these horns, sending them to infinity on 2 focal planes that are separated by dichroic. So we have these 2 focal planes observing the superposition of the beams of all horns sent to infinity. So if we had only 1 horn in QUBIC, all horns being closed, then the image we would see on the focal plane would be the beam of the horns, the Gaussian beam of the horns. Now, if we have two horns open, we start to see fringe pattern. So you can see that this is an actual simulation for QUBIC, and that's a measurement we have done in the laboratory recently. If we take two other horns open, we have another fringe pattern, and that's this different fringe that you can see here. And now the normal operating mode for QUBIC is to open all horns simultaneously, which means that the combination of all these fringes produces this very complex synthesized beam that has multiple peaks, which is a very specific originality of QUBIC. And that's the prediction, and that's the measurement we have done in the laboratory. Okay, you can find a lot of details about that in this series of papers that will be indicated all along my talk. So this is a picture of the instrument as it was at APC. So you have an idea of the size here, and the different subsystems were built by our very skilled collaborators all over the different labs in QUBIC. I will not cite all of them, but the subsystems are absolutely amazing. And we have been able to test QUBIC over the last 2 years. And what we have shown is that we really have an instrument that has the expected behavior. And we have also demonstrated bolometric interferometry in the laboratory, namely the synthesized beam, the fringes, and things like that I will show you now. So as I said, the instrument has been shipped to Argentina some weeks ago and is currently traveling. So let's hope everything goes fine in the shipment. We plan to have 3 phases of operations with QUBIC. The first one that we will start at the end of the year is what we call the technological demonstrator phase. So the instrument we're currently shipping doesn't have the full number of bolometers and has also a reduced number of horns, 64 horns instead of 400, meaning that, of course, our sensitivity is significantly reduced with respect to the what we call the full instrument. But the idea is to demonstrate on the sky bolometric interferometry by doing spectral imaging, especially spectral imaging that I will discuss later, on bright galactic regions to show these very specific capabilities. So then we will upgrade to the FI, the full instrument. Most of the subsystems for the upgrade are already available, and we're starting soon the manufacturing of the TESs. So basically everything should be ready by 2023. So we will be able to do this upgrade. Then we anticipate phase 3, where we could increase QUBIC considerably, hopefully based on the success of the previous phases, but this is still to be defined, and I won't discuss it today. So I want to discuss briefly about the systematics with QUBIC. So this is some part of our time-ordered data where we have changed the orientation of the half-wave plate, and you can see that if you zoom in, you see this modulation, sine wave modulation from the calibration source we're using, and you see that the amplitude of the modulation, of course, depends on the orientation of the half-wave plane. So this is not the maximum here, but this is close to minimum where you no longer see the half-wave plate, indicating that we have low cross-polarization. So why am I insisting on that? Because thanks to this very specific design, you see our TSEs here are not polarization sensitive. And this is an important part, because this means that because we're selecting one very specific polarization here, right after the window, there's just the half-wave plate in between, which has very low cross-pol. Then any cross-polarization that could occur after the polarizer is not really relevant for us because we have full intensity bolometers. So the cost is to lose half of the signal, but the result is really that we get an extremely low cross-polarization, and you can see here that we have a cross-polarization below 0.6 at 95% confidence level, which is really a very good achievement. So we're quite happy with this design that was really invented for having low systematics. So another important aspect of systematics handling is self-calibration, which is a very well-known technique in classical interferometry. And the idea is to use redundant baselines. If you can observe the signal from these two baselines, one after the other, independently of all the others, because they are the same Fourier mode on the sky, you should obtain exactly the same signal. And if you don't have the same signal, this can only be explained by the presence of systematics. Okay, so you will model all of your systematics through Jones matrix elements. And then you have to invert this very large problem once you have observed all of your calibration source with all of your baselines. And you can show that you can reduce by orders of magnitude the E to B leakage coming from systematics. Of course, what's important here is that the amount of reduction that you achieve will depend on the amount of time you spend on self-calibration. So this reduction here was shown in that quite old paper with just 2.5% of the observation time. And of course, we can tune that with depending on the amount of systematics we observe in our data. So now I want to show you a little bit about the synthesized beam that we have with QUBIC. So what's important here is to understand that we form this beam by the superposition of the image of all these horns and their interference range together. So the animation I will show here shows how the synthesized beam forms by adding baselines together. So this is not just adding horns, but adding baselines. And you see that when you have one baseline, you have this fringe, and when you start to have many more baselines, you start to form this very specific fringe superposition that is this synthesized beam with multiple peaks. So if you do a cut of this beam, then you see that there is this so this is for bolometer at the center of the optical system. You have this bright peak at the center, then you have these replicated peaks all around, and the distance between these peaks really depends on wavelength and on the number of horns you have. Similarly, the resolution of these peaks depends also on the number of horns and the wavelength, okay? So the second one, the orange one, is for an off-axis TS. So this is slightly different. So this means that each of our bolometer has a slightly different synthesized beam, but some variation around the same shape, basically, okay? So this is the measured synthesized beam that you can find in this paper compared to the ideal simulation. And so this means that when we're doing map making with QUBIC, we have to deal with a very specific problem where instead of having basically one in each row of the pointing matrix, we have something much more complex, and we have to deal with that. So we nevertheless solve the map making through the classical inverse problem technique by minimizing the residuals in TOD space. But our operator here really contains all the complexity of the synthesized beam, including systematics that could be better known through self-calibration, as I was mentioning before. So you can build a very detailed version of your operator here in order to converge to the best solution that is close to the sky with minimizing systematics. So this is an example of end-to-end simulations showing the input IQU, the output IQU from our from our map maker, and the difference here, which is rather consistent with the white noise. So one specificity here that has to be well understood, that is really important to emphasize, is that because we're somehow deconvolving from the fact that our synthesized beam has multiple peaks, it means that our noise is not white at the end of this process. And because we're removing negative values at some distance from the direction where we're pointing at, well, we expect to have anti-correlation of the noise at the scale of the distance between two peaks. And that's exactly what we observe when we calculate the two-point correlation function in angular space of our residuals. You see that at 150 gigahertz, we find this negative correlation exactly at the scale of the distance between two peaks, and this scales very well at 220 gigahertz. And this is measured on end-to-end simulations. So this means that in L space, we have the same noise behavior. Okay, if you transform this function that we fitted here on this data to L space, then you get this very weird shape of our noise that instead of being white noise in L space, has this strange shape. And the very nice thing here is that we have a quite significant reduction of the noise precisely at the scale of recombination, which is a very nice virtue of this peculiar noise. Okay, so this means that we achieve quite good noise in the region we're interested in. Now let me talk a little bit about spectral imaging. So the idea, I think you got the point because I somehow insisted about that earlier. The distance between two peaks here depends on the wavelength. It's proportional to the wavelength. So you have information about wavelength or frequency in the time-ordered data. So this is the map of our synthesized beam, simulation here, data here at different frequencies, and you see how our synthesized beam shrinks when you go to higher frequency, okay? And that's really important because that means that you have simultaneous spatial and frequency domain information. For instance, if you take these two frequencies, you see that you really have this peak that is clearly separated. So imagine you observe with QUBIC a source that has some flat spectrum, and you just make a scan in theta angle over this source. Well, the TOD will basically look like that, and you will see this flat region here with a peak here at the center that indicates you where the source is located. So you have the spatial information, and the amplitude at different distances from this source will tell you the spectrum of this source. Okay, so you do have this information. And basically this information can be disentangled as long as the distance between these two peaks here is more than their width, okay? And so you can, this way, measure your full width half maximum in frequency space. And this is typically 3.2 gigahertz at 150 gigahertz for the QUBIC final instrument. For the technological demonstrator, it's a bit less because we have less horns. It's about 8 gigahertz. Okay. So this is a simulation, end-to-end simulations of our total intensity and Q-Stokes parameter at in the 220 gigahertz band, just to emphasize the effect of dust. And you can see that with one single time-ordered data that sums all throughout all our wideband that goes from here to here, we can reconstruct 5 subbands with a perfect reconstruction of the dust signal here that is evolving with frequencies, both in total intensity and Q or U. And we can do the same, of course, at 150 gigahertz. The price to pay with that is that, of course, you have a strong anti-correlation and both correlation and anti-correlation between your bands. And this is something that is shown here, where you have the I, Q, and U covariance matrix or correlation matrix between our different subbands. And you see that we have significant anti-correlation with the next band, which has to be taken into account when you do component separation or whatever. This is basically the same that is shown in L space here with some L binning each time for the different cross spectra between two bands. So this is a more complicated matrix, but you see that it has basically the same structure. So one result that we're particularly happy with is the one I'm showing now. So this is the same synthesized beam that I have shown before with the animation at different subbands, but here with different colors. The blue is the highest frequency, the red is the lowest frequency, and you can see that we do have this ability to separate the colors that I think can be well seen with this image. And what we have done for this data set is we have used our calibration source set at 150 gigahertz. We took data and then we reconstructed using spectral imaging into 5 subbands. So the the 5 subbands are defined here. And you can see that we indeed see the source very brightly at the 150 gigahertz subband, and with very low power in the other bands. And now, if we measure the intensity with just an aperture photometry around the center here in each of the band, we get the red measurements here. And the blue line here is a prediction of our frequency resolution from the calculation that I was describing before, 8 gigahertz, just from the number of horns that we have. And you see that it is extremely consistent. So we're very happy to see that the spectral imaging not only works on simulation, but also with real data. And we're eager to see that with sky data, of course. One important feature when you're playing with this kind of thing is to be sure that this is nearly optimal. Because of course, we could do, if we do 100 subbands, well, probably we will be far from optimality, and then we will not gain anything. So this is the study that has been conducted here, mostly by Louise Mousset, my PhD student, reconstructing the tensor to scalar ratio as a function of the number of subbands, and comparing the error on the scalar on the tensor to scalar ratio to the one band, which is shown here. And so this means that and this is divided by square root n again. So if we had perfect square root n behavior of the spectral imaging, which would mean optimality, we would be on that line here. So you see that we're not exactly optimal, but not far from being optimal, meaning that we do gain significant spectral information when we do spectral imaging. So I want to insist on one point here. There is no specific hardware for spectral imaging. This is just a software trick, right? This is just that you reconstruct your data onto more bands. As I was, I don't think I really discussed this. Basically, the idea is to write the same map-making problem, but as a sum of different operators operating on skies at different subfrequencies. Okay, and so that works quite well. And one point is that in that case, the integration time is not shared among all the subfrequencies and not shared between the detectors. So you don't have this usual loss when you're trying to do spectra of the CMB, because you need bolometers at different frequencies, or you need to spend time at different frequencies with the FTS and so on. So this is a clear advantage here. I'm coming to the last part of my talk, and I think I should hurry, basically. This is the forecast we have. So because we're doing maps at different frequencies with subbands, this is the kind of results we could expect with QUBIC in the future, where we have a map, and in each pixel of this map, we can measure the spectrum of the sky. Okay, and so that is with total intensity near the galactic plane in the clean patch that we anticipate to look at, which is the same as the bicep one. And you can see that we do see quite clearly the foregrounds here, and that's in polarization as well. You can find all of this in this draft here. So coming to the tensor to scalar ratio, that's the shape from Monte Carlo of our error bars in L space. And the dashed line you can see here is basically obtained from the curves that I was showing to you before. Sorry, these curves here that are transferred to the same units as in this paper, in this plot here. And you see the dip in our noise around the recombination scale, which is quite a good thing. And from this, we can obtain these forecasts on our sensitivity to the effective tensor to scalar ratio. By this, I mean that we didn't attempt to do any component separation here. So this means that it's the resolution we have on the combination of tensors and foregrounds. And we're currently working on applying component separation with various techniques. But of course, because of these correlations that I was talking about, it's a bit trickier for QUBIC than for actual instruments. Just one last thing I wanted to show is this nice feature we can have with spectral imaging. If you imagine that you have an experiment that measures, say, say in your broadband, you measure R equals 0.05 here in the 220 gigahertz band as an example. You measure R equals 0.05, but you don't know if this comes from CMB or dust. Well, if you do spectral imaging here, just 2 bands, you see that you can do 3 interband cross spectra, and you can measure the effective R as a function of the effective frequency. And you can see that if it's dust, well, you can see the slope. In that case, it was 0.7% dust residuals, which is detected at the almost 3 sigma level, while with tensors, you would not detect any slope. So that gives you an extra way of constraining your contamination from dust. Well, I think my conclusion, I should stop here because I've been talking too much already. And well, this is just essentially what I've been saying so far, so nothing new here. And I leave you with this series of 8 papers that we have. Oh, there's one missing. Sorry, I forgot one. I forgot the one of the papers, the number 4, which is there. Sorry, it's just I will add in later.